son says this computer shit.
All right, so this is the entire story of registers. Are there any questions about registers before we move on to something that's kind of has more details in it? Yep, go ahead.
So you said that registers aren't memory, so what exactly are they?
Sorry?
You said that they aren't memory, so what
They are a
exactly
part of the processor core. So when you install, modern processors have multiple cores, but each core has its own set of registers. So that's the other nice thing about it is, if you have 4 different cores on your processor, there's never any contention as far as registers are concerned, because each core has its own set of registers. Good question. Any other questions regarding the use of registers, or why we even have registers? Yes, go ahead.
Basically, they just kind of they're not memory, but they're like kind of like a cache.
They're not cache either. Cache is transparent for the most part. In other words, you cannot, for most instructions, as far as an application is concerned, you have no control over what is cache and what is not cache. It's a transparent mechanism where the hardware will automatically figure out what should be stored in cache and what should not. Registers, on the other hand, are under your direct control. So every instruction specifies, I want this register, I want this register, I want this register. But it's not memory because it is not going all the way out of the processor, going through the memory bus, go to your DIMMs to access memory. So it's not memory, and it is not cache. It is a unique, independent construct inside the processor core. Yep.
How would they go registers?
Registers, in this class, the way I teach this class, we're only using the 32-bit mode. So each register is only up to 32-bit wide. When you run your processor in 64-bit mode, then you have 64-bit registers. We'll talk about this part because what we see as a 32-bit register, a lot of times can also be seen as 16 and 8-bit registers because of the long legacy of the Intel processor. In order to be able to be backward compatible, it has to be able to do that. So we'll talk about how to dissect a 32-bit register into smaller chunks, and each of the smaller chunks can be considered as a register. Any other questions? Those are all very good questions that will be answered later in the class, in the semester, not this class. All right, so we're going to move on to memory access. So this part is going to be a little bit lengthy. So we only have about 22 minutes to go, because originally I was about to say, oh, let's take a break, but we'll just keep going. The freight train is not stopping. All right, so what we'll do is we'll start with the discussion of memory chips, and this one requires a little bit of a picture thing, so I'm going to draw some pictures on the whiteboard. If you want to take a picture, that's fine with me. Without going into hardware details, the main memory of a computer is usually implemented by multiple memory chips. Each memory chip has a certain storage capacity, usually measured in bytes. The external interface of a memory chip consists of the following. I'm not even counting the power and the ground lines, which is irrelevant in a class like this. So it has what we call address lines. It has data lines. It has one line that is labeled read-write, and it has a chip select line. The pins corresponding to the address are input pins. In other words, they can only serve as input to a memory chip. Each pin accepts a binary input, meaning ones and zeros. And typically, the convention is a high voltage means 1, a low voltage means 0. Together, the address pins specify an address on the chip itself. For example, if a memory chip has A0 to A9, in other words, 10 address pins, then it can specify location 0, which is in decimal, to location 511, which is in, I got this wrong, didn't I? Because this should be 1023. Because there are 10 bits here, 2 to the power of 10 is 1024. So I got this wrong. I got to fix this. So in other words, let's imagine this is 1024, and then we have 10 bits here. These are correct, but this one is incorrect because this should be 1023 and not 511. Okay, but nonetheless, we're still using 10 individual bits to specify a location on the memory chip itself. Okay, so at this point, we're going to use an analogy, and I usually pick on people on the front row, because they sit there because they want to be picked on. It's like over at Marine World or Six Flags, why would someone sit in the front, in a killer whale show? They want to be splashed. So here's the splash. Okay, the splash is coming. Okay, so let's say we have 4 memory chips in the system. Okay, so what it is you have your 1,024 locations in memory. You have your 1024 locations. You have 1024 locations. You have 1024 locations. So these are my memory chips. When I specify, and all the address lines are connected. Okay, this is one really important part is they are sharing the same address lines. So when I say location 700, you all heard that. Okay, you're all hearing 700. So now the question is,
Which one?
which one, right? Yep, exactly. That's the purpose of the chip select line, because the chip select line says, oh, I need your location, not the other 3 chips. Okay. But I just want everyone to be aware of the fact that each chip has the address lines, and all the address lines are connected together. Each location of a memory chip is an individual quantum to access. In other words, you cannot access any quantity smaller than that. And typically, it is usually a byte, in a smaller architecture. In the Intel architecture, in most motherboards, it's no longer a byte. Okay, when you're accessing memory, the data bus is what, 64-bit or 128-bit wide? I think it depends on the generation of the processor. It used to be, when the processors were 32-bit, it was already a 64-bit data bus. So in other words, every time we access memory, we're accessing 64-bit at a time. But for the discussion of the memory bus, we'll just assume that we're dealing with 8-bit data bus. Okay, each time I want to access something from the processor's perspective, I'm only accessing 1 byte or 8 bits at a time. The data pins of a memory chip must be wide enough to input or output the content of a location. So in this particular example, we have 8-bit and 8-bit data bus. So you have an 8-bit data bus, you have an 8-bit data bus, 8-bit data bus, 8-bit data bus, or data pins. And all the pins from the data pin, all the data pins are connected. Okay? So if one of you, say, 23 is the answer, we can all hear it. Okay? The other chips as well as the processor can hear that when one chip, is putting something onto the data line. It works the other way around too. If I want to store something and I scream, 45, all 4 memory chips can actually hear 45. Once again, the chip select line is the important one to specify which one of the 4 memory chips is supposed to store the content 43. Okay, so we'll get to that part too. So I'm just giving you a preview here. This means that if a location is a byte, then we can expect 8 data pins. Usually they are labeled D0 for bit 0 of the data line to D7, which is bit 7 of the data line. Data pins are bidirectional, which means it can be driven by the memory chip or it can be driven by the processor, depending on whether it is a write operation. If it is a write operation, it is going to be the processor who's driving the line, and it's the memory chip that is sensing the line. If it is a memory read operation, then the processor will be sensing, and then one of the memory chips will be driving the line. Does everybody understand what is sensing and what is driving?
Could you repeat that?
Does everybody understand what I mean when I say driving a line versus sensing a line?
Explanation.
Oh, the explanation. Okay, all right. So we have 4 memory chips here, okay? And I have an 8-bit data bus, okay? Each memory chip has 1024 locations. Okay. If I want to write something to store back into memory, the processor, which is me, will be driving the data lines. In other words, I'll be specifying the content on the data bus. High, low, high, high, low, low, high, low, okay? So I'll be specifying the voltage on the data lines. The memory chips, or one of the memory chips, will sense that the voltages and write that content into the memory chip itself. Okay, so in that case, I'm driving the line, the memory chip is sensing because all it's doing is to sense the voltage on the lines. When I'm executing a read, then it's the other way around. Because one of the memory chips will be driving the data lines. So one of the memory chips will specify, high, low, high, low, high, high, low, high, on the data lines, and the processor will now be sensing, what are the voltages on the lines, so I can, grab that and put it into the ALU for processing. Okay. So what if, for whatever reason, two memory chips decide to drive the lines at the same time, and they're not driving the same, data either. So let's say, you and you, decide to output, 1 something something something, and you decide to specify 0 something something. What's going to happen in that case? First of all, this is called a bus fight, okay? And I'm not kidding, that's a technical term, it's called a bus fight, okay? A bus fight happens when only one chip is supposed to drive a particular line, and somehow you ended up with more than one chip, driving the line. Now, if both of you are specifying the same, data, you're both trying to drive the same line high, or trying to drive the same line low, it's not a problem, okay? It's only a problem when one wants to drive it high and one wants to drive it low. In terms of electrical engineering, it means one is sourcing the current and the other one is sinking the current. Okay? When there are no resistors to limit the current, then the limitation is only going to be the transistors, right? Okay? So in that case, at least one of the two chips will burn out. And that's why bus fights are really not good, unless you're talking about a bus that is designed to have fights. Can someone name a bus that is designed to have fights? No jokes from the real world, please. Yeah, I know that 82 line of light of RT is supposed is a good it can handle bus fights. I've seen it. Okay, so can anyone imagine in networking this is called CDMA? No, I cannot remember the name. Okay, so which networking standard is designed to handle these kind of fights?
Oh,
Ethernet, very good. All right, somebody has the answer. Ethernet is supposed to be able to handle this kind of fight because what happens is Ethernet has no management of who gets to speak next. Okay, there's no such thing as saying it's not systematic. Okay, so two computers hooked up to the Ethernet, especially in using a hub, can say I want to talk, but I want to talk too. Okay, first of all, how do they know they have a bus fight? Because I got this bruise, so I can I can tell it's a fight. No, because they listen to itself. Okay, each NIC network interface card. Not only is it trying to drive the line, but it's also sensing at the same time. It's trying to listen to what it is to the line. So if it cannot hear back what it is actually saying, it's garbled, then it knows there's a fight. Okay, another NIC is trying to talk at the same time. So how do we resolve this? We'll take it outside, right? Take it outside of the bus. Then we can determine who's going first. No, they have a much worse.